Good morning to all. So we will continue our design of brake system. Today learning outcome would be we are going to discuss about braking efficiency and braking distance or stopping distance, and also we are going to learn about brake factor. So these are the two topics we are going to cover or discover, and understand in today's lecture. So braking efficiency, right? The braking efficiency is the ratio between your maximum deceleration rate to the road adhesion coefficient. Yeah. So the braking efficiency, you can have a eta b equal to the maximum deceleration rate, depends on is it front axle or rear axle, and with respect to road adhesion coefficient mu s at ground and tire interface. So that's how it happens. So what do you expect? Okay, when your deceleration rate, right, is matching with your road adhesion coefficient, what do you expect? The brake efficiency will be 100, right? The brake efficiency would be 100. That's where you will get your minimum stopping distance. S is a minimum stopping distance. You may ask question, so what happens my deceleration rate is less than your mu s? What do you expect? Your efficiency braking should be less than 100%, right? So what is the consequence? What will be the consequence? Your deceleration is not matching the road adhesion coefficient. So what happened? It will struggle to reach the stopping distance. That means you will have a more distance. The stopping distance would be more. Stopping distance is not minimum, will be more. Okay. So another question is, do you think is it possible to have braking efficiency more than 100? Is it possible? Yes or no? No, right? You can meet. Remember, so you can able to meet exactly 100%, not beyond that. The beyond that, what happened, right? So this is your, assuming it's your reaction force, then this is your braking force, right? This is what happening, and this is moving in this direction, assuming that, and of course you have all the other forces I am not going to show, right? This is rolling. So when you say self locking, the self locking supposed to be mu equal to PB equal to mu s into n. This is what happened, right? This is the way. This is the where condition you will expect the self locking. Self locking. When do you expect? Until then, the wheel keep rotating, right? When the moment reach, it will stop. What happened further? It should drag. It should start skid or should slide. When do you expect sliding or skidding? This should be more, right? Your braking force should be more. Then only that can be achieved. The skidding or sliding can be achieved. Okay. So please understand. This is about the braking efficiency. Now it's a very important parameter. Okay, what are the dimensions? What are the engine power, torque, or size of the braking your brake system? Either it could be disc brake or drum brake or combination of both. Doesn't matter. You have to maintain the minimum stopping distance. That is very critical. That is very critical. Okay. Now we will discuss about the braking distance aspect. So for braking distance or stopping distance, okay, it depends on two things, right? Your deceleration rate, the stopping distance in differential equation form. I am just going to give. What do you expect? Your deceleration ds, right? The deceleration again depends on your braking effort Pb plus summation of all resistance. Remember this we discussed earlier. Then when vehicle moves, right, when a vehicle moves, so you have energy, kinetic energy is there, but again there are certain components. I am talking about, let's say, certain component, your clutch, gears, universal gears, all those rotating will have initial effect also, right? That has to be taken care of that. Okay, the translation masses which give the another energy, that is also you have to take care of, that is Km W by G. So this is what happened into ds, of course. So this the rate of velocity with respect to dv, which is your equivalent to your acceleration aspect. So the Km is the correction factor for rotating masses. Rotating masses in the vehicle. Usually it vary 1.03 to 1.05. We will discuss more when we go for a thermal analysis. The thermal analysis, this term will come into the picture. Okay. Then the determine the stopping distance, to determine from initial velocity. What is the initial velocity? V1 to a final velocity V2, right. So when you want to do that, this would be, just I am rearranging, ds equal to V1 V2 Km W by G into Vd Pb plus, right, sigma r. This is got, maybe we can say this is equation number 1. Okay. What is the r? It's a tractive resistance, right? This all r is sigma r tractive resistance. I hope you remember mu r W cos theta, that is one term. The another term would be plus or minus your gradient W sin theta, okay, aerodynamics RA, and your transmission resistance also there. All these things sigma r, total resistance when the vehicle is moved, right. This is too small, so we can negligible. Too small, so obviously you can neglect, that is absolutely fine, right, that is absolutely fine. Okay, the equation is everything given Vd by, that is so with the integration of V1 by V2. I want to understand, yeah, the, right, the RA aspect, this RA aspect. This RA is a aerodynamic resistance, or air resistance, right, aerodynamic or air resistance, right. What is it? RA of rho CD AF V square. This is the equation, I am sure you will know that. Where rho is the density of air, okay, and CD is the with drag coefficient, and AF your frontal area, vehicle frontal area. Okay. I will give you problem with this aspect, vehicle frontal area aspect. How when you change the vehicle frontal area, the RA will change. Then further how RA would affect your braking. So I will give one problem in assignment. Of course, V is the vehicle velocity. Right. So among this term, your density constant, your drag coefficient also constant for given one shape, your frontal area also constant. So finally, it's a V square. That is the one is a variable, right, for braking. So what I'm going to do, I will combine all this term as a CAE, coefficient of aerodynamic resistance. I can see that with the V square with respect to RA. Yeah, with respect to RA. So then my sigma R, if I rewrite, will be mu R W sin theta, sorry, W cos theta plus or minus W sin theta plus C A V square. So this is where, right. So I am going to substitute this one into the main equation 1. If I do that, ds equal to V1 V2 P V dV. So this is PB mu R cos theta plus or minus W sin theta plus V square. This is what happened. Okay. So now V dV is given. Also we have a term V square, and there is a limit V1 V2. If you do integrate, finally you would expect the equation, the Km W by 2G, right, Ln. This is a simple integration. I am sure you would know these things. PB mu R W cos theta W sin theta and V1 square. This is V1 square PB mu R W cos theta plus or minus W sin theta plus this should be Vt square, right? That should be Vt square. This the limit is given. Okay. Again, if I do the simplification, okay, we'll come back to simplification. So the V1 is the vehicle initial velocity, V2 is the vehicle final velocity. What is the V2 generally? Generally V2 will be 0. V2 equal to 0. So if we substitute that one in this equation number 2, okay, you expect this distance, stopping distance Km W by 2G. This also constant, right? I take it out and again I simplify that. If we do that, finally I expect 1 plus V1 square divided by PB mu R W cos theta plus or minus sin theta. So this is the equation number 3. So this is your the stopping distance of vehicle. So you look at this, it is related with the Km, the vehicle weight, then aerodynamic coefficient, right. Finally the braking effort PB, your mu R nothing but a rolling coefficient of friction, right, rolling coefficient mu R. Then the initial velocity V1, I think I missed one term here, it should be W sin theta. This is what happens. Okay, fine. So this is fine. This is okay. You know that when do you expect the braking efficiency will be 100%? When do you expect? When PB equal to mu s into W. That is the way its braking efficiency will be 100%. Ln, right? Yeah, sorry. I think correct. Ln is that term I missed it. Yeah, correct. Thank you. Right. So I'll move now. So when the braking total braking effort PB equivalent to mu s W, at the time your braking efficiency will be 100%, right? 100%. Not only that, the rotational of the masses also will be equivalent to the Km also will be equivalent to 1. So in that case, your minimum distance S minimum, okay, from equation 3, S minimum equal to W 2G CAE ln 1 plus square. Here instead of PB, I will write mu s W mu r W cos theta plus r minus W sin theta. This is the equation happen. Okay, if the braking efficiency 100%, but generally the braking efficiency won't be 100%. It's always less than 100. NB always less than 100%. In this case, the S minimum, the distance would be W 2G CA ln, right, 1 plus V1 square. The only term would change will be in the mu s W, I will add my efficiency also, not add, yeah, I multiplied the braking efficiency into mu s W mu r W cos theta plus or minus W sin theta. So this is the equation, yeah, this is your stopping distance equation, okay, for brake. Fine. Let me ask question. This is in actual condition. In reality, what happened? What do you expect? Should we not consider the reaction time of the driver? Right? The reaction time of the driver also should be considered. By the time you will you covered certain distance, right? That is also there. So some distance already covered in the reaction time. Normally the reaction time vary with the fraction of 0.5 seconds to 2 seconds maximum, right? Then you apply a brake suddenly. So by the time you would have crossed certain distance also. So that is also you have to consider when you calculating for stopping distance, right? This is absolute condition. The braking distance whatever we find now, the minimum distance is absolute, but in reality we have to include the driver reaction and the consequently the distance crossed during that time. Okay, yeah. So this is for your braking distance aspect. Now we'll move on to the brake factor. I just want to recap again what exactly happening, right? We know that we got mu s is your road coefficient, right? Road addition coefficient. Road addition coefficient, that is already known to us. Fine. Mu r is the rolling resistance, rolling coefficient. Mu l, where is it? Where is it coming from? It's a question of friction of brake lining, right? Of friction brake lining. brake line. Okay. We know that the vehicle is moved right on the road surface. Yeah, it's moving in this direction, right? The W G by A, then your deceleration rate also will be there. Then I'm just going to show this. This is W. It's happening, right? So when it's happening, this the PB will come here. Your reaction force will come into the picture. So we know that this is entire kinetic energy, right? Whatever you see, we're talking about is the entire kinetic energy of the vehicle. This is kinetic energy of vehicle. Yeah, this is kinetic energy of vehicle. Okay, so you will have a brake torque. The brake torque coming from would be from vehicle. Brake torque is coming from. Right, that's fine. Okay, this is one aspect. So when I want to stop the vehicle, the entire kinetic energy should be matched with the friction energy, right? Entire kinetic energy should match with the friction energy. Then only the dissipation happen, the vehicle can stop. Until then, vehicle cannot stop. Okay, so entire kinetic energy must be equivalent to my friction energy. Okay, so it has to be equal, right? So you will have a torque, brake torque from your vehicle. Then there is a brake torque from your brake. This is from brake system. This is from brake system. This is from your vehicle system. Both are different, right? So now I try to understand. This is coming from where? This is from your pedal force, right? This is from pedal force to vacuum booster. Vacuum booster to where it goes? Master cylinder, right? Master cylinder. Then what happened from master cylinder to a brake circuit, right? Brake circuit, from brake circuit to it goes two direction. One is your disc brake system, other one is your drum brake system, right? Can you see that? One we are coming from the pedal force to where it's going to be brake, whether it is disc brake or drum brake. That's a one thing is there. So that's one aspect. The other aspect, the vehicle is moving. When a vehicle is moving with the mass, right, with the kinetic energy. So where we are talking about the vehicle weight, the vehicle dimension. We are talking about a vehicle dimension including wheelbase, tire, right, the tire diameter, the frontal area, all those things come into the picture. So that has to be matched. Now I wanted to interlink them. So how this exactly will be balanced based on the which component or which parameter? That is based on your friction lining. That is the one generating the friction, right? Not no other component, right? So an entire energy you are talking about from the vehicle, then entire brake or friction energy should come the brake system through friction lining. So the question is, we never discuss anything about the mu L, right? Did we discuss anything? And also, how do we know what is the value do we need to match this kinetic energy? So that's where the brake factor will come into the picture. Now can you see that how the interconnection, what is happening, right? From your when you are applying the brake, right? When you are applying the brake to your brake system, right, to activate, then the kinetic energy happening through vehicle, through your wheel and road addition factor need to be balanced through your friction lining with the corresponding friction value. So that we have to find out what would be the mu typically for given the vehicles. Okay, this one it depends upon the what type of brake system are you going to use it. That's what we are going to discuss about the brake factor aspect. Yeah. So the braking wheel and the drum brake torques. The maximum braking wheel torque is limited by your wheel slip. Wheel slip in the sense the wheel rotate, the moment you reach to the maximum braking torque, the wheels try to skid or slide. That is what it means to say the slip aspect. Okay. The second thing is the torque produced at the brake drum caused by frictional force between the brake lining and the drum to bring the wheel to standstill position. That is one aspect, right. The two things are there. Yeah, both the wheel and drum torque must be equal at the point of wheel slip. Understand now? So, it has to be equal, but should be in opposite direction, should be opposite direction, then only the vehicle can stop. Yeah. So, that both torques are equal and vehicle will stop. Okay. Now, we will move on to what exactly going to happen. We will understand the shoe factor and brake factors. Okay. The shoe factor, the ratio of the friction force. Now, we are talking about with respect to drum brake system, talking about drum brake system. We will discuss for a disc brake also as we move on. The shoe factor is the ratio of the friction force at the drum radius to the activation force P at the shoe tip. That is one thing is there. The brake factor is the combined effect of two shoes. Normally, when you say drum brake there are 4 types, right. Drum brake will have a 4 different. What are they? One is leading and trailing, right. So, that is why 2 shoes are coming. The another one is leading. Yeah. What is the third one? S-cam, right. S-cam also there. S-cam will have both leading and trailing shoe. Then other one would be servo dio, right. Servo dio. So, the 4 types, okay, the 4 types are there, but we are going to for understanding we will choose only one drum brake system, which is the leading and trailing aspect. With that, we will try to find out what would be the shoe factor and the brake factor. From there, how it is select the corresponding friction lining for the given vehicle. Yeah. So, I am going to choose a simple one, leading, trailing, brake drum. Very simplest way. I am not going to do very complex. So, but I will give a problems very complex way in assignments. This is your drum, right. This is your drum. Okay, you take it as a radius R, drum radius R. Okay, I am sure you know this is the pivot. From the pivot, you will have a like this. Okay. From the pivot, this is a shoe arrangement. So, the distance from the pivot to the where the tip the force going to activate is a C, which already known to you. That is there. So, I am just showing only the small amount of friction lining, because the entire thing is a friction line, but for our understanding we are going to choose only small area. Just for schematic purpose, do not take it as very as per the dimension things. So, assuming that this is moving in this direction, okay. So, but I want to give you information from the pivot to the center of the drum, the dimension is given as a uh, n, I will give you as a n, okay. Then from the pivot to center of the thing, again from the pivot to, okay, this is a distance, this is vertical distance from pivot to the edge of the drum, right. This distance is given as a m, right. So, when you are applying the force, the tip force, right, you would expect obviously two forces, you know that. One is your normal force Fn, where we have taken as a Mn there. Your the frictional force is coming here. Frictional force Ff is coming. This is what is there. The two things are there. Okay. So, what we are going to do, we will take the moment. Take the moment around, similar to what we did earlier, the shoe point pivot, we will take it as a pivot A. This we are talking about whatever shown is only for the leading shoe aspect, not the trailing shoe. Whatever we are discussing now is a leading shoe aspect. So, when you talk about A, right, P into C plus F m f n must be equal to 0. So, just I try to balance the forces momentum aspect. So, finally, okay, we want to do the P c plus f of m. I will move this term n f n. Okay. Whereas my friction lining mu l is depends on the your friction force to the normal force, which already known to you. This is, please understand that. Okay. Mu l equal to friction, coefficient of friction of brake lining, brake line, yeah, that is there. Then P c plus f m equal to n f n, but I already know mu l equal to, because we want to find out the mu l. So, this is your f f by f n. If you substitute, you will expect n into f f by mu l. I am just simply replacing f n with this equation. I want everything bring in terms of my shoe factor. The shoe factor is nothing but SF is the friction force ratio of the friction force to the activation force, Ff by P. Okay, Ff by P. Thus, I just wanted to, from here already we know this are assuming this is the equation. From the equation we can finally derive at maybe I can even more, I will simplify that. If we do that 1 minute, the FF will come. One second. Mu L by C n minus m into mu L. I am simplify that. Of course, one more term I forgot to mention, the activation force nothing but your Fn. The activation force is nothing but your Fn. Equal to your Fn. If you do that, so you would expect the shoe factor SF for the leading mu L C n minus m into mu L. This is for the leading shoe factor for leading. My question is, what happened trailing? What do you expect trailing? The same term will be there. This instead of minus, that will be positive. Okay. SF trailing we will see, right, n plus m into mu L. So, this is the one things we would expect. This is the trailing. So, when you talk about a brake factor, is nothing but summation of leading shoe factor, the summation of trailing shoe factor. This is what happened. This is what happened. Maybe I would have rewritten here also, you can see that. That is fine. I think this is clear to you. The brake factor equal to the shoe factor of trailing plus shoe factor of both need to be added. Similarly, this is if you have trailing, leading it will be 2 times, right, and so does for S-cam as well as servo dio also. In fact, we can see the comparison, and see this I have taken from brake design and safety by Rudolf Limpert. You can look at this. This is a mu L, okay, this is the mu L, right, the corresponding the brake factor, you can see that. Okay. So, we will look at the first the trailing and leading, right. For one question of friction, maybe we will choose 0.5. If we choose 0.5, you would expect in the range. Any reason for this? Why the brake factor will vary upper value to lower value? Any reason for this? Any reason for this? What is the reason? Right, it is a leading and trailing. What is the reason for that? Think about that. So, similarly, if you look at for the 2 leading, again 0.5, right, if you use the mu L, you will expect the range, wide range, okay, wide range. Then as a within among that, the servo dio has a better brake factor. You can see that the servo dio has the better brake factor than leading and trailing and leading and trailing. So, this the arrangement is clearly given. For disc brake, you could see that the maximum is given 1.2, that is a value, and the single value. Any reason? The arrangement is disc brakes is the pad, calipers, right? Either you have circular pad or annular pad. There is no leading and trailing. So, then you do not get a range, right. So, straight away it is a fixed value. And one more thing is there any self locking in disc brake system? No, right, there is no self locking, okay. But you have self locking in a drum brake system when Mn equal to Mf. Remember the one initially we have derived the equation. So, you will have self locking, which is not advisable, okay. The question is, then the brake factor is good for leading and trailing, whereas disc brake will have a lesser brake factor, but has a no self locking. Then what is the reason we are still using a trailing and drum brake system? That question will come, right. So, there is one more term is called stability. You have to look at stability also, right. You have to look at the stability aspect. In fact, again this is the reference I am giving you from taken from brake design safety by Rudolf Limpert. Look at that. We are talking about disc and pad. The maximum shoe factor you would expect 1.2, right. The stability is good, whereas if you have a stability is good, okay, stability good, whereas if you have leading and trailing shoe, the brake factor is good, but the stability is not enough. right. Again, if you look at the two leading shoes, the brake force is really good, right, but the stability very low. The duo servo has also very high brake factor, right, but it has a very low thing. Okay. Now, do you know the reason now why the drum brakes are fitted at the rear and the disc brake are fitted at the front? Remember, one of the dynamic analysis we have recommended, we have to design the brake system always for a front axle lock first. Front axle lock first. Okay. Let think about the scenario. Instead of disc brake, if you expect the drum brake at the front, what do you expect? Instead of disc brake, the drum brakes are fitted at the front axle. What do you expect? First of all, they have self locking, right? They have self locking. They have self locking, right? So when they have self locking, even then, if it's front axle lock, do you think that will be better? Do you think that will be better? You can replace the drum brake with the disc brake, that is allowable, because even then you have a less back factor, but the stability is better. You always look for the stability, that is very critical, because it is a reliability component. Brake system is a reliability, it is a life of death and catastrophic thing, right. So that has to be taken care of while designing. That needs to be taken care, that should be addressed. So you can always replace a drum brake with a disc brake. If you do the vice versa, that's going to affect the stability and leads to catastrophic failure. Now you know that, okay. In fact, the modern vehicles nowadays come all four wheels with the disc brake, right. So that's how the brake needs to be taken care of then, okay. I think I'll give you a problem. Before that, now you can see that. So now you know the friction lining clearly mentioned. We have from the analysis. So based on the SAE coefficient of friction code, we are given the various category C, D, E, F, G, H. That's like that. Now you can see that the C has the lowest coefficient of friction range. As the grade is improving, the friction range is increasing. Okay. Again, I am asking a question. Instead of giving one single value, why the friction lining is given as a range? What is the reason is given for a range? Why can't I have one particular value? What is the reason behind? What is the reason? Right. Then that is where we talk about thermal analysis. Okay. The brake can be applied various aspects. Either you can have a single stop braking, repetitive braking, or drag braking. Based on that, your coefficient of friction will change. Right. So if you have applied sudden brake, it's a single brake. Right. That's one way of applying a brake. Otherwise, if you keep apply release, what happens? You are allowing the system to cooling down. There, your friction requirement will be different. Okay. Similarly, if you move on to the downhill, so what downhill the friction, the brake requirement will be very different. So when you talk about the vehicle will undergo different condition. So when you have different condition, you need to have different coefficient of friction. So rather having one single coefficient of friction, you should have a range, such a way that to cater all the situations. Yeah. Okay. So this is the way you have to select. In fact, we are going to do a problem. I think the time is very limited, so I am going to stop now, but we will continue tomorrow.